SwayamPrabha. Digital India. Educated India.
Welcome to lecture number 11 of the Statistical Thermodynamics course. So this will be our first dabble at quantum mechanics, which we said is needed to find out quantities like energy, EJs and GJs basically. It's a long path, so just bear with me for the time being. So what happened was this quantum mechanics is a little abstract, so we will try to follow a more historical perspective till we get to the Schrodinger's wave equation. So what happened was that in 1900, Max Planck showed that the classical theory of oscillating electrons could not explain the behavior of black body radiation. So he showed that classical theory of electrons, of oscillating electrons cannot explain black body radiation. Correct. Okay. So what he did was that basically they could not explain the black body radiation spectrum. So Planck, what he did was that he devised or developed a general expression for emissive power, okay, the emissive power that conformed to the experimental data at both wavelength limits. So experimental data at both high and low wavelengths. Okay, so both the limits were basically satisfied. So he investigated a little further and he found this very unique thing, that the quantization of energy is needed to derive this empirical relation between emissive power of a black body and the frequency of its emitted radiation. So the emissive power of black body and its relation with the frequency of the emission, okay, is actually given by his empirical relation. Okay, but to derive that empirical relation, he needed quantization of energy. So he needed quantization of energy, which we always say has been the cornerstone of quantum mechanics. So what he did was that, in particular, he postulated that the microscopic energy okay, emitted at a given energy, say that, let's call that E, and emitted at a frequency, let's call that gamma, okay, they are proportional to each other, and such that this energy is given as NH gamma. So N is basically an integer. So as you can see, there is no N 1.5 or 1.125, stuff like that. This is nothing but a frequency, and this is called the Planck's constant. This is Beer's name. Okay. So the understanding is, what did Max Planck did? He looked at the black body radiation spectrum. he was able to come up with a thermodynamic relation which could explain the black body emissive power at both the high as well as the low wavelengths. Now, the aftermath of that was he found that if his empirical formula has to be explained properly, then the emissive power and the emissive frequency or the wavelength, okay, they are basically quantized. So based on this, he postulated that the microscopic energy E emitted at a frequency gamma is basically given by this particular form, where n is an integer, so this ensures the packeted nature of the energy, and h is the Planck's constant, and gamma is the frequency. So what happened after this? So this is a quantized. So the energy is quantized. Okay, quantized energy. Also, as a corollary of this, okay, you can also say that the radiation is composed of distinct entities like photons. Okay. Radiation is composed of distinct entities, okay, like photons, okay, like photons. The energy is h nu. Okay, like photons. Now, Albert Einstein, what he did? So Einstein, in his photoelectric effect, he tried to provide an explanation of the photoelectric effect. So what did Albert Einstein do? Okay. So the photoelectric effect occurs when electrons are ejected from a metallic surface as a result of bombardment with ultraviolet radiation. So if you have UV radiation bombarded on a metallic surface, okay, this is a metallic surface, you give out electrons. Okay, you give out electrons are ejected. So what did Einstein do? He took this Planck's newly minted expression, okay, and suggested that the incident radiation behaves not as a classical electromagnetic wave, but as discrete packets or discrete entities or photons. So he said, so incident radiation is not continuous by any stretch, but it is composed of photons now, which has got energy, which we already said, of h nu. So each photon, this is the energy of each photon. Okay, so when the ultraviolet radiation strikes a metallic surface, what will happen? If you just take an energy budget, okay, so the maximum kinetic energy of the dislodged electron, let's call it Tm, will be equal to h nu, that is the energy that is carried by each photon, minus some phi, where phi represents the minimum energy required to remove the electron from a particular surface of a particular material. So this is the energy that is needed to dislodge or move, whatever you call it, dislodge the electron from the metallic surface. So this is the minimum energy. So when people actually did the experiments, we found that, okay, this maximum kinetic energy expression is quite valid. This agrees with the experimental data. And interestingly, this particular maximum kinetic energy depends on the frequency and not on the emissive power. So that was very interesting. So this Tm depends on the frequency of radiation, okay, and not on the emissive power, where we eliminate it. Okay, not on the emissive power. And this relationship is linear. It's linearly dependent. More is the frequency, more is the kinetic energy of the dislodged electrons. Okay, so if you let me put it formally, this is the kinetic energy of dislodged, the maximum kinetic energy of dislodged electrons. So Einstein was able to provide this beautiful explanation. Okay, but this actually revamped the corpuscular theory of light, which has been there, proposed by Sir Isaac Newton, but it was abandoned shortly because of the investigation of Young and Fresnel. They showed that the radiation or light actually exhibits both diffraction and interference. That could be explained beautifully if we model light as a traveling wave. And then subsequently, James Clerk Maxwell said that light behaved like an electromagnetic wave. So hence, that viewpoint of corpuscular theory was abandoned for a short period of time before Einstein actually revolutionized it, okay, and said that indeed the photon is actually quite revolutionary, and it actually is, it does not go by the classical theory of electromagnetism or light in general. Okay, so that's some kind of an historical perspective that how this was done. Okay, so however, so Einstein's seminal work suggested also for the first time that there is something called wave-particle duality of light. So it is like a metamorphosis of some kind, that sometimes light will behave like EM or electromagnetic radiation, right? Okay, in which the light will behave like a wave, and it will show interference, diffraction, which has been all proved. And then sometimes it will act as particles. Remember, the photons are actually bosons, sometimes as particles. Okay, and when the particle nature of the light dominates, okay, the radiation is discrete. This leads to the discrete nature of radiation. Okay, so this gives rise to the discrete nature of radiation. Okay, so this also subsequently means that the material, okay, emitting or absorbing light undergoes distinct change in energy, undergoes a distinct change in energy, which is given as delta E, is given as H nu. Okay, so the discreteness comes over here, that the material that is emitting or absorbing light undergoes a distinct change in energy, which is given as this. Okay, now subsequently what happened was that when all these things were going on, okay, Rutherford actually proposed that the atom is composed of a central nucleus, and then you have the rotating electrons. Okay, so this is some kind of an atom model that was proposed by Rutherford. But immediately people jumped into it. This is because the electrons are basically charges. So a charge which is rotating, which is moving, right? A orbiting electrons should therefore radiate, gradually lose the energy, and basically spiral, and bam, it should merge with the nucleus. So the atom would be a very short-lived entity, which it is not. It is very stable, as we know, because you needed a Manhattan Project basically to split the atom. So this was quickly abandoned as well. This is because it could not be reconciled with classical mechanics at all, or classical electromagnetism. It could not be reconciled because the orbiting electron should actually radiate energy and should actually coalesce with the nuclei. So here came Niels Bohr. So what he suggested, and gradually became known as the Bohr model. So he said that there is a nucleus. Let's call it nucleus, and then there are these orbits, which is called electrons, rotating in those orbits. So electrons orbit at fixed radii. This was the Bohr model. So what did Bohr suggest? He provided basically he refined Rutherford's model a little bit. He added a little bit of a twist. He said, building on Einstein's work, that the electrons actually orbit at fixed radius, and discontinuous transitions between orbits occurs when only photons are absorbed or emitted by the atom. So what will happen is that if you now bombard this atom with photons, which is called energy of this, the electrons can actually go from higher or lower radii, so they might change their orbit. Okay, if and only if photons are absorbed or emitted. And the transitions will be discontinuous. They cannot go to a slightly lower orbit and start orbiting. It cannot happen. This is not permissible. They have to absorb a fixed quantity of radiation to move to a higher orbit, or they have to lose a fixed quantity of radiation for them to move to a lower orbit. But these transitions are all discontinuous in nature. Transitions are all discontinuous in nature. Okay, only happens when photons are absorbed or emitted. Only happens when photons are absorbed or emitted. This model offered the first comprehensive explanation of a known spectrum of atomic hydrogen. Okay, and we will see how that was actually done. Okay, the amazing agreement between this particular Bohr's model and the spectrum, okay, for the first time suggested that how the quantum mechanics can be reconciled with spectroscopic observations and and how it actually deviates from the classical or accepted form of electromagnetism. Okay, so so that was the Bohr's model. Okay, now let's look at the hydrogen spectrum. The hydrogen spectrum is obtained in those days by a hydrogen lamp and passed through a prism and then onto a photographic plate. So if you look at the spectrum, so that is like a spectrograph. As you can find out, so let's draw it properly. So you can see that there are a few lines like this. So this is around 912 angstrom. This is about 1216 angstroms. And we move a little further. Okay, so this is 3647 angstrom. And this line, which is 6563 angstrom. Then you basically have three more lines, okay, which is 8206 angstrom. And this is the final line, which is 18760. So this is called what we call the Lyman series. This is in the UV. This is called the Balmer series. This is in the visible. You see the distinct lines, right? The line name. This is called the Ashton series, which is in the infrared IR. Okay. So these were the lines that were. There are three series of lines. Detected by the spectrometer. Okay. So these are the three sets of lines that were detected. And if you look at these particular lines, they are very closely spaced. Okay, they are very closely spaced, and then there are these large separations as well. Okay, so there is a dense form of the line, and then there is this characteristic reduction in line spacing. Okay, so the upper and the lower limits of each spectral family is between this to this. Then, of course, Bastion is about from 300 and Obama is from 3647 to 6563, and so on and so forth. Okay, so at this juncture, we introduce a convenient spectral definition. We introduce a convenient spectral definition, okay, which is called the wave number. It's got a unit of centimeter inverse. So the wave number is written like this, which is basically equal to this by C, which is equal to 1 over lambda. Okay, so we have recognized that the wavelength is basically this. Wavelength is, as we know, C by the frequency. So the wave number is basically just the inverse of the wavelength. The utility of the wave number indicates the number of vacuum wavelengths in 1 centimeter. Okay, that the discrete energy changes are directly related to the inverse of the measured spectral wavelength. So that's why this is a very convenient definition that we are going to use over here. So employing this particular definition, the discrete wavelengths of all spectral lines that we have seen over here, okay, all spectral lines in figure this can be empirically correlated via the Rydberg's formula. So if you look at the NN2 transition, it is like given by the Rydberg formula, 1 over m squared minus 1 over n squared. Okay, m is equal to 1, 2, 3. This is an index which represents Lyman, Balmer, or Bastion series, okay, respectively. N, on the other hand, is basically n plus 1, n plus 2, n plus 3, so on and so forth. This identifies okay, the spectral lines of each series, and the Rydberg constant, which is RH. So the Rydberg constant, and this is one of the most accurate constant in physics. The Rydberg constant is written as 109,678 centimeter inverse. So, ideally, whatever theory that you propose, it has to replicate this particular equation. It has to conform to this particular equation. It also has to predict this particular constant. Okay, because these comes from very precise measurements that we can see, right? So as you can see, so any formula that you propose in, or whatever ways you want to propose, it has to kind of obey that particular thing. Okay? Accurate reproduction of RH is actually needed. RH is actually needed for the success of the Bohr model, which ultimately invoked energy quantization because of the two integers. So this is energy quantization is inbuilt because of the two integers. Integers m and n. Okay? So because of these two integers m and n, this is already inbuilt, okay, quantization. So the success of the Bohr's model would mean Bohr's model will be successful if and only if it can predict this gamma Nm and RH. If it can do that, then we, on a prima facie basis, we will call it a success. So Bohr's model was nothing but Rutherford's model with a twist, where he said that the electrons actually rotate in fixed radius. They cannot give out energy continuously. They can only go from one orbit to the other, which would be like a discontinuous transition or a discrete transition, when only there is an interaction with photons of fixed energy, which is h multiplied by the frequency. We also introduced the concept of wave number. So the wave number actually is the inverse of the wavelength, is the number of vacuum wavelengths per centimeter. So essentially the wave number is an important concept because it allows us, because as we saw in this particular thing, that the energy transitions, okay, from is directly discrete energy changes are actually related to the inverse of the measured spectral wavelength. Okay, so that is the beauty of the thing. So and all these things came, this energy packeted concept that energy is equal to nh into the frequency, came from Planck, who actually modeled the entire black body radiation spectrum and found that he cannot reconcile it with classical physics anymore. So he had to take resort to basically what he did was came up with an empirical thermodynamic relation, and that led to the fact that if that relation is correct, then energy has to be discretized, and he could match it at both the higher and the lower wavelengths. Okay. Those two things were independently matched by Rayleigh and Jeans, but nobody could match the whole spectrum, okay, in that particular case. And Einstein was able to use this, and he postulated that, okay, this ultraviolet radiation that hits the metal surface is composed of photons. This photon comes and bombards the surface and gives out electrons, and even the kinetic energy of those electrons could be accurately linked using the theory that was proposed by Albert Einstein. So this revitalized the particle nature of light as well, and so it was inferred that light actually shows wave-particle duality. So sometimes it behaves like a wave, sometimes it behaves like a particle. So in the next class, what we are going to see is that we look at the Bohr's model and try to understand that how the Bohr's model can explain, this particular formula that we just wrote here. Okay, can we explain the spectrum of atomic hydrogen? So see you in the next class.